In this video, I'm going to talk about the synthesis of alkenes. And so this is going to kind of be a lot of the same stuff that I've been talking about in the previous couple videos. It's mostly done with elimination type reactions on alkanes and specifically on halogenated alkanes, so haloalkanes, and as we'll see on alcohols. And so just as a reminder, an alkene is just just carbon chains with double bonds in them. And so we have the two p orbitals here. These overlap, we end up with these pi bonds up here, which gives us a double bond between carbons. And I already did the video on nomenclature for alkenes as an earlier video back when I was talking about the alkanes as well. So I'm not going to go through the naming in this video. So we'll just talk about the alkene synthesis here. So yeah, one way of doing this is dehydrohalogenation by the E2 mechanism. And so we want to have particularly our anti-coplanar here. So this base will take that hydrogen off of there. The electrons will move to that bond to form the double bond, and then the leaving group will leave there. So we end up with a transition state that looks kind of like this, where we have all those partial bonds there, and then we end up with the base now being protonated and our leaving group having detached, and we have the double bond here. So with a bulky substrate and strong base, E2 is favored over the SN2. So that's because if we have bulky groups on here and right here, this isn't going to be able to attack that carbon as easily, so we will not see that as much. So this will attack that hydrogen there, it will move the electrons down there, and then we will have our leaving group leave here. And so this will be greater than 90% of our product here. So the other 10% being something like the SN2 product, so the nucleophilic substitution product. So if the substrate, though, favors an SN2 reaction, then we can use a bulky base instead to try to force the elimination reaction. So if instead we have a hydrogen here rather than the bulkier methyl group, we can use a base here. So this base here, this tert butoxide, which has these bulky groups on it, which make it more hindered, and so it won't be able to attack that carbon as easily. So it won't go to here as easily. So instead, we'll take this hydrogen, the electrons go down here, our leaving group leaves, and we form this double bond over here. And this in the box here are just some common bulky bases that are used for this this E2 reaction rather. So like the diisopropylamine, the triethylamine, the 2,6-dimethylpyridine, and the tert butoxide, which is what we were showing up here. And so if we have a substrate that favors the SN2 reaction, then we can use a bulky base in order to hinder it from performing the SN2 reaction, and we can get our E2 reaction in order to form the alkene, which is, what this video is about, is the formation of alkenes. So we're interested in getting that elimination reaction. And so this is just an example of using the diisopropylamine here to do one of these reactions. So this will have a lone pair on it. We can have this come down, take that hydrogen, the electrons move there, these ones move onto the leaving group, and so we end up with the cyclohexene right here, and then this protonated base right here. And so that's just a particular example of performing that reaction. So we can also try to get what are called the Hofmann products. So as I've been talking about in previous videos, we usually get the Zaitsev product, which is the one that is the most substituted. So this one up here is the tri-substituted, where this down here is only di-substituted. And so we're using this ethoxy base right here. And so that's going to go and attack this hydrogen right here more often, having the electrons move down here, and then these go onto the bromine, where if we wanted the Hofmann product, we'd have to attack right here. And so what we can do in order to do that is use a bulkier nucleophile. So up here, we're just using this ethoxide right here. Down here, we're using this tert ethoxide right here. And so this is going to be hindered from taking this green hydrogen right here, and so it's going to favor going after this blue hydrogen right here. Electrons going down there, these ones going onto the leaving group, and now we're going to favor the Hofmann product rather than the Zaitsev product. And so we can use these bulkier nucleophiles to get the Hofmann product over the Zaitsev product. Again, the thing to notice is in both cases we're getting a mixture of both of them. So we're getting 71% Zaitsev here and 29% Hofmann here. We're down here, we're getting 28% Zaitsev and 72% Hofmann. So you're not getting 100% of one or the other, and that's something that it happens quite often in organic chemistry. And so if you want to get one or the other of these, then you'll have to do some sort of separation method to get to separate these out from each other. And I will probably do a few videos at some point in the future where I talk more about some of these laboratory techniques for separating things and stuff like that. But for now, I'm just sort of going through, I guess, the theory of all this stuff. And so the take-home message for this is we can use this bulkier nucleophile to favor the Hofmann product over the Zaitsev product, because it's going to go after the less hindered hydrogen there. So if we look at the E2 reaction, we can look at the stereochemistry of the E2 reaction. We see that it's stereoselective. And so here in this Fischer projection, I have this molecule with both chiral centers being R. And so that's going to look like this if we look at it from the side. And so when we rotate this around those bonds, we get this right here. And so we see this base will come down, it will grab that hydrogen, the electrons go down to form the double bond there, and the leaving group then leaves. And so we end up with this cis isomer here. And we can see this in our Newman projections as well, where this base comes, takes that hydrogen, the electrons will go down to form the double bond there. This will leave, and it will sort of push these two things together in that direction so that these are cis from each other. Whereas if we go from the RR chiral centers here to the SR down here, we see that we will actually get the trans isomer as the product here. So it's going to look like this. We twist it around that bond so that we get this. This comes, takes the hydrogen there. The electrons go to form the double bond. This goes there. We see we have this phenyl group pointing towards us, this one pointing away from us, and so we end up with the trans double bond here. And so we can do the same thing with the Newman projection that goes there. This goes down to form the double bond. The leaving group leaves. We see that these are going to sort of crush together like that. So we have the phenyl group on this side on the carbon pointing towards us, and this phenyl group on this side on the carbon that's pointing away from us on the Newman projection. And so, yeah, the E2 elimination mechanism is stereospecific. And so we can look at this in cyclohexane systems as well. So if we look at the chair conformation, so I have the axial here drawn or written in green, where the equatorial are written in black. And so the axial ones are, it's called trans-diaxial, and so they're pointing away from each other. And so we can actually get that anti-coplanar geometry for it. So in a chair conformation of a cyclohexane ring, a trans-diaxial arrangement places the two groups anti and coplanar, as I just said. So we're going to form the double bond here between these two as we remove this hydrogen, and this bromine then leaves. And so we can see that here. So if we have our base come in, it's going to take that hydrogen, this goes down to form the double bond, and this leaves right here. Or we can look at it from this angle right here, where this comes, the electrons go to this to form the double bond, and the bromine leaves. And so the hydrogen and bromine in this chair conformation are anti-coplanar from each other. And so we can get these E2 reactions to form our alkenes. So there is also this E2 debromination of vicinal dibromides. And so we have this Fischer projection here. We see we have this bromine here and this bromine here, giving us our vicinal dibromide here. And I just noticed that I actually have this S and R flipped around on here. So this should actually be the S, and this should be the R right here. And so that's the S and R chiral centers right there. And so if we look at it from the side, so if we look at it from this side right here, we will get this right here. We can rotate these around this bond here so that we get it in this formation right here. This iodide is going to bond with this bromine. And so the bromine, the electrons from this are going to go down to form the double bond there, and then this one is going to leave. And so we actually end up with this IBr right here. So the iodide actually bound with the bromine there, and then this bromide left. And so we get this trans stilbene here. So that's talking about these two phenyl groups here. And so that's the trans stilbene from that. And so we can do this debromination of the vicinal bromides using this iodide like that. And so that's another way to form alkenes. We can also do the dehalogenation by E1 mechanism, which I've already discussed quite a bit in previous videos, so I'm not going to go through it in too much detail here. But remember, we get this leave like this as the rate limiting step. So this is that slow step right here. So we end up with the carbocation. Then we can have this base take that hydrogen, the electrons go down to here to form that double bond right there. And that's the E1 mechanism. And this is, of course, in competition with the SN1 mechanism, where this base instead goes to that carbocation. But as I've discussed in previous videos, you can do things with your base. You can use certain bases, for instance, that are bulkier so that they become inhibited or hindered from attacking that carbocation in order to push for the E1 mechanism. And so we can also, so these E1 dehydrohalogenations, as I've discussed in previous videos as well, are prone to rearrangements. And so what we can see with this top reaction here, so this bromine is actually bound to this tertiary carbon. So when that leaves, that tertiary carbon here is actually going to be the most stable. So what we will see are these two elimination products here and this SN1 product here. So if this ethanol actually binds to the carbocation, then we'll see this SN1 product right here. But we can get these two elimination products here, where we see this one up here is the di-substituted one, and this one is the tri-substituted one. And so this one right here is going to be the major elimination product, because we're going to pull the hydrogen off of this carbon right here in order to make the tri-substituted elimination product. But if we then instead have this bromine, the leaving group on the on this secondary carbon here, what you'll see is that you'll get hydride shifts. So there's a hydrogen coming off of here, and so you'll get hydride shifts as that switches over there in order to produce the carbocation on the tertiary carbon. And so when we do that, so one thing we will see is we can get the SN1 product here if we have the hydride shift, or we can get the SN1 product here if we don't have the hydride shift. So if the carbocation stayed on that carbon, then we could get this SN1 product right here, where we see that if we get the hydride shift, that we can get well, we could get to this product right here with the hydride shift, because if the carbocation moves to this tertiary carbon, then we could pull a hydrogen off of this carbon to make this double bond right here. Whereas this one right here could come whether we get the hydride shift or not. And so we could form this one whether we get the hydride shift or not. Then this one right here we would only form if we did not get the hydride shift, because we would need that carbocation on that carbon right there in order to form the double bond right here. And so yeah, we can get these hydride shifts in this E1 mechanism here. And so I'm going to go over here. So now we're going to look at what's called the acid-catalyzed dehydration of alcohols. And so this is one that I haven't really discussed much in previous videos, but we can form these alkenes from actually removing this alcohol group here with an acid-catalyzed reaction. And so if we use H2SO4 here, we can do this, where we have the alcohol group, we have this come and pull a hydrogen off of here. The electrons will go onto there, and so we end up with this right here, with this positively charged oxygen. And so then what we can do here, so we have this slow step of the water leaving. So this will go here, we lose the water, so we can put plus H2O here as that leaves and forms this carbocation. Then we can go down here and we could have a water come in and pull this hydrogen off. The electrons come down here to form that double bond, and so we end up with the hydronium ion here and our alkene right there. And so again, this is going to be the rate limiting step where we are forming the carbocation. So again, the water here is acting as the leaving group, and so that's going to be the rate limiting step for forming that carbocation, which is going to be the very unfavorable reaction. So this is just looking at a particular instance of this. So we have this 2-butanol here, and so we can have this oxygen come and take a hydrogen from the acid right here, and so we could then have our plus HSO4 minus right there. So we've protonated our alcohol right here. So this is in fast equilibrium, meaning that we can do this, but then we could also have probably not this H2SO4, but probably something like a water come in here and take it back off. And so, this is in fast equilibrium. But sometimes, and I say sometimes because this again is the slow step, you might actually have this come off of here. So the electrons go onto there to form a water. So we're forming an H2O here, and we're forming our carbocation right here. So that is the ionization to carbocation. That's that rate limiting step. And then we can bring in a water here, and so it could take one of these two hydrogens. So we could have it come and take this one right here. Those go down to form the double bond, and then we form that double bond there. Or we could have this come and take that green one right there and have this come down to form the double bond. So we see that taking the one from the primary carbon here is going to be less favorable than taking the one from this secondary carbon here. And so the 1-butene is going to be our minor product, where the 2-butene, which could be either cis or trans, is going to be our major product there. And so, yeah, those are just some of the methods for making alkenes. I made this table down here to sort of sum up some of these ways of making alkenes. So the ones we've talked about in this video and a bit in previous videos, so we have the dehydrohalogenation. So we have our base here, come take that hydrogen there, go down to form the double bond. This then leaves, we form our alkene. We also have the dehalogenation of vicinal dibromides, so we might use something like iodine. It binds with that bromine. This goes down to form the double bond. This goes and leaves. We form our alkene. We get our leaving group here, and our that iodine and bromine bound together. There is also dehydrogenation of alkanes, which I didn't really talk about in this video. I'll get into that in probably in later videos when I'm talking about the when I'm kind of talking about the reverse of this, which is the hydrogenation of alkenes. But you can also do dehydrogenation of alkanes, which is the reverse of that. And so using this catalyst and heat, we're going to remove these two hydrogens here to form H2, and we will get our alkene here. Then, of course, the one that I just talked about is the dehydration of alcohols. So we want this as our leaving group in an or in an E1 reaction. Then we'll deprotonate this to form the double bond, and so we're forming this water and our alkene here. There are also, and this is one I haven't talked about, I'll talk about it probably more in future videos, is the Hofmann cope elimination. So we see this is, similar to what we've had before, where we're going to pull this hydrogen off right here, and this will be our leaving group right here. So that's leaving right here, and we're forming our alkene right here. So that's just another way of forming an alkene. We also have what's called the Wittig reaction. So we're sort of just transferring this this oxygen onto this this phosphorus right here. Then this group is going to be transferred onto this carbon right here. So we end up with this alkene product right here. Then this will be the double bond oxygen will be transferred onto that phosphorus right there. And again, I'll talk more about that in future videos, but this is just kind of a summary of ways that it is possible to actually form alkenes. And another one that we didn't talk about, but it's a way of forming alkenes, is the reduction of alkynes, which are these triple bond carbons here. So we're using this palladium here, or this barium sulfate, as the catalyst along with hydrogen gas. And so the hydrogen is going to sort of bond across there. So one of them will bond to that carbon, the other one to that carbon, and so we will get this cis alkene here when we use that method. If we instead do a reduction using sodium and this ammonia, or ammonium here rather, we're going to then make the trans alkene. So I actually should have switched it so that I had the R prime right there, because that's the trans alkene there. And so again, I haven't talked about these in any detail, but these are just ways that you can form these alkenes. And so, yeah, the ones that go here, so the dehydrohalogenation, which is just that E2 reaction there, the dehalogenation of vicinal dibromides, the dehydrogenation of alkanes, which is just the reverse of the hydrogenation of alkenes, which I'll talk about in future videos, the dehydration of alcohols, which I discussed in more detail in this video, Then the Hofmann and Cope eliminations here to form alkenes, the Wittig reaction to form this alkene right here, and then the reduction of alkynes, there are two methods, one to form the cis-alkene and one to form the trans-alkene. But anyway, those are ways that we can form alkenes. In the next several videos after this one, I'm going to talk about reactions that we can actually do with alkenes. So once we have our alkenes, what can we do with them? So what kind of reactions can we do with them? And so that will be the topic of the next several videos after this one. But anyway, I hope you found this video helpful, and I will see you in the next one.